Okay. Okay, so I wanted to talk about robotic simulations. And so, first of all, the reason why you'd want robotic simulations, robotics are difficult in the fact that you have to deal with, not only you have to deal with software, but you have to deal with the hardware side of things. You have to deal with electronics and mechanical issues. And when you're trying to write code to run a robot, and then you're finding out that I'm not even sure if my code's working or not because my computer's resetting because I'm low on power, or this motor, my left motor is turning a little harder than my right motor, and you want to be able to eliminate those kind of concerns. And one of the best ways to do that is with simulating the software on your simulating the robot on your computer. Also, it's great for repeatableness. Say I have a vacuum cleaner robot, and I want to ensure that it can get around a certain obstacle every time. So I can set up a simulation with a certain type of chair that maybe has thinner legs, and maybe another simulation where it's going under a table that's not quite tall enough that I find it gets stuck on. And as I update the software, I can rerun it on all these older simulations and verify that my new changes to fix some new problem didn't break some old problem that I used to have, without having to manually test the robot. You can also run simulations, multiple simulations simultaneously. You can run them in the cloud. You can run them at faster than real time. So I'm just going to talk about a couple of tools that I use for simulations, and show a demo of how that works. Okay, so the first one I want to talk about is Gazebo. So Gazebo is a physics simulator specifically designed for robotics. I get the impression it can be used for other things also, but it's mainly developed by the Open Source Robotics Foundation, and so it's really specific to robotics and ROS, which I know I've talked about ROS many times here, but I'll talk about it once again in a few slides. So I want to show some quick videos of kind of what Gazebo looks like. But basically, it's a place where you can create a real-world type simulation, and you can place your robot in there, and you can send input to the robot that would be the same as the input that you would send to a real physical robot, and you'll get feedback from the robot that would be the same as the feedback you would get from a physical robot. So a couple things that it does. So this is the Space Robotics Challenge. This is a challenge that NASA did, what was it, about a year ago, maybe two now. And let's see, oh man. Okay, so give me 1 second. Let me restart this timeout. This was happening the other night too, when I was testing the presentation. Sometimes the YouTube videos don't play. So let's see. They broke my remote clicker too with the last update. So, okay. There we go. Go back into it. Okay. All right, so this is showing basically NASA set up the simulation with the, I don't know if this is the R2 or based on the R2 robot. And this is a Mars environment, so they're able to set even the gravity and everything to be what it would be like on Mars. And this is a robot going into a space station and completing several tasks. So they had a contest where, so they have this simulation pre-set up, and then when you enter the contest, you basically just had to write the code to get the robot to do several tasks. So you saw them adjusting a radar dish. Now he's going into the habitat. There's I believe a gas leak inside the habitat, so the robot needs to pick up a tool that's designed to find this leak and search for it and then repair the leak. So you can see, like, on the tool, it had that like cone-shaped, I don't know, those lines coming out of it. That was like part of the feedback of the simulation. Like if you have a sensor on this gazebo, you can get visible feedback of like what the range of the sensor is. So if you're not sure if the robot can see walls or obstacles, you can visually determine that.
Do you see through the eyes of the first person, through the eyes of the robot, or?
You can actually see. Well, actually, first person probably is the one view they really don't have, because it's meant for seeing for watching the robot. So most of the time you use third person, but you can also do a top down view for like a flat navigation robot.
So that's not part of the programming, in other words. You're not programming it using the visual feedback.
No. So yeah, that's the one part I want to try to clarify in this talk, and is that Gazebo is separate from ROS. Gazebo is for getting feedback from the robot. It's a replacement of your hardware. So you're supposed to be able to drop in this software in place of the hardware, and the software should give you all the feedback that the hardware would normally be getting, and it should receive all the input that the hardware is normally receiving and respond to that in this virtual world. So let me show another real quick. These are only like 1 minute long videos. This is also Gazebo, and this is a self-driving car simulation, just to show the all the different features it has.
Red stop sign.
Hasn't killed enough people yet.
But it does simulate human behavior quite well.
Yeah, just like I tried.
No turn signal.
No turn signals and road to stop signs. Yeah, perfect.
Cut corners.
Now I should go off in the grass, though.
Yeah.
So you can see a little feedback from LiDAR there, those blue dots. This is showing a better view of that. Yeah, so the important thing is Gazebo is not doing the driving. It's not controlling the car. It is just simulating the car so that you can write your own software to try to control a car and to test it out instead of just...
So does it require ROS, or can it work with any multitude of inputs?
Oops, I didn't want to do that. It doesn't require ROS, but I haven't really seen it used without ROS. It's developed by the same people that develop ROS, so it's really biased. Although there's a little weird stuff I might talk about like, although it's developed by ROS, they use a different file format for their robots, and there's a converter, and it's like I don't understand why they don't share the exact same file format, but I guess there's some technical reasons for it. So Gazebo has plugins that you can make, so you can create sensors like the cameras, GPS, sonar. You can actually get visual feedback from your cameras if you want to use something that does some kind of visual optical detection. It'll be a little cartoon-like, so I'm not sure how that will simulate the real world. Lasers are really useful. I've used that one a bunch. Sensor noise is also another real useful thing that Gazebo does. So if you've worked with real world robots, you don't get clean data. If that's 10 meters away, you're going to get 9.9, 10.1, whatever variations. You can actually feed that information into Gazebo saying this is the quality of my laser, this is my environment, then I want a little bit of fuzzy data to make sure that my robot can actually handle that. So
They were using LiDAR on that car. This may be off topic, but
Mhm.
it looked like, I'll call it 3D LiDAR because it looked, as opposed to 2D, which is one beam.
yeah.
Do you have
Like
any
a
idea?
dome?
Yeah, like a dome. Do you have any idea what that might actually be? Or,
What the 3D LiDAR is?
yeah.
I think it's just 3D LiDAR. I mean,
Yeah, I guess I'd have to look it up.
because most of the 3D LiDAR I've seen is really a 2D LiDAR, and they just spin
They
it.
spin it and then
And
they
then-
shoot the LiDAR that mirrors angle.
Mhm.
And so they shoot the LiDAR up and down the
Oh.
mirror
Mm.
really
Okay.
fast.
That's what I was trying to picture
Yeah.
is how many projectors or what are they using to but that makes more sense.
Yeah, they're just working on one. I know some people are working on solid state LiDAR, but I haven't seen
There's a
it
new,
in
I got a chip
production.
that is, I haven't tried it yet, but it just came out. It was like $10, but it's a LiDAR, dual sensor LiDAR that's good to 12 meters.
Which for what we do, that'd be good.
It'd be perfect, yeah.
Mm.
You can spin it, it's only like $10. So
Huh.
there's a lot of things coming out, and I should have brought it, but.
Yeah.
uh,
You can think of the name, we'll look it up later.
Yeah, I'll bring it, yeah, I can find it.
Okay. So, like I said, Gazebo is designed for ROS, and just I'm not going to go deep into ROS, but a quick overview. ROS is a robotic operating system, but it's not really an operating system. It's more of a bunch of programs that run inside of an operating system. So, ROS will run on different things, but it's really designed for Ubuntu. They have a lot of stuff that like integrates with the Ubuntu package manager that like loads dependencies and stuff. So you could use it in other operating systems, but you'd have a rough time. I think it possibly works in Windows, but you'd be fighting against it all the time. It's just better off using it where it's designed to run. So yeah, it's tools, and it's also conventions. So a lot of ROS is like just saying, if I want to send like laser data to my robot, this is what the format should look like. So if I'm sending it, now I can have any program I want that receives it, as long as they understand it's going to look like this. Let's see. Okay. And yeah, the important ones are topics and messages. So topics are, okay, so anytime I'm sending data from one node in ROS to another, and nodes just being programs that are running inside ROS, I use a topic. And so like my laser scanner, which we saw in the previous video, so I would send that scan data on the scan topic. So that goes into a, well, in this case, with the way ROS does it is, my scanner would start transmitting or register itself with the master and say I'm transmitting on the scan topic, and then another program that wanted to listen to scan data would ask the ROS master, say I'm listening to the scan topic, and the ROS master would then basically allow them to connect directly to each other. That's actually changing in the new version of ROS, ROS 2. They're switching to a message queue system. I think they're using a 0MQ. So I think that'll allow like multicasting, and they won't directly connect. Well, actually they might, so I'm not going to get into that.
They also offer guaranteed delivery too if they go to that.
The 0MQ, well,
Yeah. So it'll hold if a node goes down and there's messages, it'll wait till the node comes back up and then send the messages to it.
yeah, I wasn't sure if 0MQ did that. I have more experience with like RabbitMQ.
Yeah.
I've used that one, but when I was reading a little bit, 0MQ looked like it kind of don't the clients talk to each other directly? There's not like a server involved.
Yeah, it does, but each server, if it has messages, it'll queue messages up for so long locally if it can't get to one of its listeners. If it
Okay.
just goes away, it doesn't deregister.
It just handles that itself.
Yeah.
So, okay, and then the messages are basically a predetermined format that they would send it in. So if I'm sending like a command to control my robot speed or something, like the command to do that is command velocity message, and it's got basically 6 floating point values for like turn speed and forward velocity and things like that. So I actually would prefer that they got rid of some of the messaging or made predefined messages optional. I think they could send like raw JSON or something like that for most purposes. It's fast enough, but anyway. Okay, so putting this all together, if you start up Gazebo by yourself, it's just you get like this blank world and there's not a lot going on to it. And I was gonna show like an older demo of like Willow Garage. I don't know if everybody's heard of Willow Garage, but they're kind of the ones that started all this. They created the PR2 robot. This was maybe over 10 years now. I don't know how long it's been. But they actually developed ROS, and I think they went under or something. And the Open Source Robotics Foundation took over. But you used to be able to get their, you could get their office layout inside Gazebo.
Oh.
But what? Oh. But then I found this just came out like a few months ago. It's like fairly cool. So the Open Source Robotics Foundation made this simulation called Service Sim, and it's a contest to get this guide bot to guide people through an office building. And so I'll show a couple screenshots. So they have this pretty involved like office simulation. It's got, it's really small, sorry, on the screen, but there's like the people walking around. So the people actually do walk around. They have collision enabled, so they can block your robot. You can control people with the robot a little bit, although they're a little bit fickle as part of the contest. So the robot is given a task to like drive up to a person. So you go up to that person. You can send a ROS message, basically that's like control this person for a while. Then that person will follow you until they get bored, and then you guide that person to their destination. So now it seems like it's a contest and a game a little limited, but this is not. This is really, as far as I can tell, designed as a demonstration of Gazebo and its capabilities. So they kind of put this contest in as a way of showing you what it can do, but you don't have to follow along with this. You can take their robot out, you can put your robot in. They have really good instructions on how to do that, and see how your robot acts in an office with people around, which is something I've kind of had problems with, because I'll run my robots at home and they're great, and then I'll bring them to the science center and like people crowd around them and they block all my sensors and the robot's lost and can't handle it. So it's kind of interesting that you can run this and get a more real world simulation. So that's just the robot taking people to a checkpoint. So their service bot looks like a walking robot, by the way, but it works like a driving robot. It's got wheels. It just kind of scoots around. I'll actually show that in a couple minutes here. Okay, so I think that's the basic intro. So now I want to show off like the demo of how to run this service sim. Okay. All right. Okay, so it's on the website that I gave in the presentation. They host it on Bitbucket, and they use Mercurial, I think it is, which is a little weird. They don't use Get. Like everybody, like 99.9% of everybody uses Get, but for some reason OSRF uses HG instead. So that's the only like difficulty as far as running it, but it's pretty easy to run. I created a little script that kind of launches the different parts. They have it broken down into different sections, like okay, always the same with the ROS master. Oops, close this out. Okay, so with ROS, you do have to have, you have to know your master's IP address, and you have to set an environmental variable, which is kind of a pain when your environmental variable, or when your IP is changed. But, okay, so I usually set it in the bash RC file, there, and so my ROS master is now 101, and my IP is 101. So I'll exit that. Source. Bash RC. Okay, so now I should have my.
ROS doesn't have a discovery service?
No, actually, that's ROS 2 is supposed to be adding a discovery service. Although I haven't used ROS 2, so it's hard for me to talk too much about it. But I've read about what they're trying to do, and this is one of the things they're trying to fix. But to fix it, now they have like either a messaging queue, or they're using like a DDS network system to do discovery. But still, you have the same. I think you still have the same issue of having to get the IP address of a master or a peer in that network. I mean, I guess it's going to be a little easier because now it can just be a peer. Like, if you connect to anybody, you've connected to everybody.
Yeah, well, what Cobra, which is like an old time, like the original granddaddy object request broker, it had a service that would respond to a UDP broadcast, just a multicast. And so you'd multicast and say, where are you? And it would listen for the multicast. You'd multicast your IP address, and then it would respond to you and say, I'm here, and here's my IP address. And then you could connect to it. So no matter where, you just brought a master up on the network, and the clients could discover.
Yeah, if you did that, some kind of broadcast system.
Yeah.
But I'm not sure that's straightforward to do, especially with the way I like to use ROS too. I use ROS a lot with Docker. So I'm using container systems where you really have to specify ports. It's like having really restrictive firewalls.
Kubernetes, so that you can run your Docker containers across multiple nodes to do that. And then, because then it would be all like in one security control.
Okay.
Which Ubuntu do you recommend? Is that even on the web?
16. Well, it depends on which. If you are using it with ROS.
That's my goal. I figure.
So it depends on which version of ROS you want to use, but I don't know, probably 18. 1604 is probably a little more compatible with stuff. You might have some stuff that doesn't work on 18.
Okay. Is ROS 2 mature enough to use yet?
I haven't really started using it. I don't think so. I mean, well, it seems like, okay, so ROS 2 just doesn't do a lot. So you have to install ROS 2, and then you have to install the ROS 1 bridge, which connects you to everything. But it's like almost everything you use needs the bridge. So why do you have this extra layer? You know, I don't know. It is out of, oh, that's what my shirt is though. It's in version B now.
Yeah.
It's out of alpha, it's out of beta. So, okay. So let's see, this guy. Okay, so this is Gazebo. This is the actual Gazebo program. Let's see if I can do this without a mouse. So you get this like 3D, it's almost like a game world. You know, you can zoom in and out. You can, my mouse battery's dead. It's really hard to control without like a mouse. I use the mouse wheel a lot, but.
Mouse.
What?
There's a mouse.
Oh, is there? Oh, yeah, that'd be
Yeah,
helpful.
and it's wired. So that makes it
Super
battery.
Yeah, to control it, use the scroll wheel and stuff to zoom in and out. You can hold down shift or the control keys to rotate around and see different things. So there's the robot. You should see people. There's kind of people walking around. You can view different things like view, I don't know, collision area. That even worked.
That's a horrible collision for a video game.
That's not actually the collision area. That didn't work. It should be a different color. So, Gazebo is a heavy program. I mean, you can. I don't know if you can hear my fan is running on my laptop, trying to keep up. I mean, it's doing a lot of calculations here. This is not.
Probably throws a lot to your video card too.
Yes, it will use your video card. I tried to use it in Docker, and I couldn't get it to work. You can use Docker and NVIDIA, which is what they recommend, but then only certain video cards actually have that feature, and I think because it's a laptop. I couldn't figure out how to find it, but I was in a hurry doing other things. So, but yeah, I think just with Gazebo, it's a little tough to do that. So you can use Gazebo as a full editor. I've seen I actually watched one presentation they gave at ROSCon where they actually did their presentation in Gazebo. They put slides in there and stuff. So you can drop in, I'm just going to drop in an ambulance just to show you can edit your world and save it and use it in other places. So, okay, so that's it. So Gazebo is now giving us feedback. Sorry for bouncing around so much. So now I should be able to see, type ROS topic. Why am I not? Sorry. List. So now I can see all these service bot messages that Gazebo's either transmitting or listening for. So, and I can control Gazebo control the robot in Gazebo by sending messages. Here's the command velocity to get it to move around. Alright, so I'm not going to do that all command line. I'll do that through the graphical interface. So if we got this Gazebo, another part of the simulation they launched. This is RQT. RQT is another ROS program that allows you to do different things like send commands. This has got a little bit of, I can control the robot through this sending velocity commands, like if I wanted to move forward. Now we look at the robot, it's moving forward. Everybody can kind of see that. So I can stop the robot. It's not really the greatest interface for controlling, but if you just need to quickly see that this is working, when I send a forward command actually starts moving forward, it's useful. I'm getting feedback from the a little bigger the cameras. So there's a rear camera and a front-facing camera, so I can see that kind of stuff. I can see logs and different things like that. And then one of the purposes of showing this is they have a custom component up here. You actually have this scoring thing. So they're just kind of demonstrating how you could keep score of a contest. So if I started the contest or started the robot on a task, the score would start counting up. Okay, so that's RQT, that's Gazebo, and then this is RViz. Okay, so RViz is another ROS program. This is one I use all the time. This is the robot visualization software. So if you're dealing with a hardware robot and you're trying to control it through ROS, this is probably all you're going to use is RViz. So this is really what you normally be able to see, and then if you have a real robot, instead of looking at your physics simulation, you can look at your actual physical robot to see what it's doing. So, it's important to think of Gazebo as not how you control your robot, it's really just how it's simulated. So this is the office that the robot is in. So it's already on. They have already set the map, so it's not creating the map. So if you can see, the robot doesn't really line up at all where the map is. So, well, I probably should explain this all more. If I turn on the model, it'll be a little easier. So there's the robot model right there. And these red lines, okay, so on this side of this screen you can see I have like my laser scan, my map. Okay, so if I turn off my laser scan, you can see that's on or off. That's basically showing me raw input of what my laser sees. We have the local cost map. The local cost map is not a real thing, it's a calculated value. So there's a part of the navigation program reads in the laser scan and it finds close by obstacles. So that's what these are right here. So that's just like visual feedback so I can understand what obstacles the robot believes are in front of it. So if it's like running into a wall and I can see that my local cost map is not seeing that wall, or more likely on my robots it would be that my laser is too high and it's hitting the table and I can see that the cost map doesn't see the table. There's the global cost map, and that's more of, this is used for like long-term planning. It's very similar to the local cost map, but it doesn't update as often, and the robot uses it for navigating from room to room. Okay, so first thing you need to do for a robot that's not using SLAM, so SLAM was simultaneous location and mapping. Since it's in a static map, you need to tell it where it is or give it a approximation of where it is. So in this thing, you just kind of visually have to look, and I can tell there's two doors there. It's kind of in that door. There's the cubicle. I think if I flip this around like this, I think this is the view that we're getting.
Well, Josh, I don't understand something here. You said you need to tell it where the robot is.
Yes.
But I thought that's the visualization that you've got was, it created that by knowing where the robot was, right?
This particular map is pre-made. It's a static map. So there's different ways to get your robot to navigate. You can use static maps if you have like a known office or warehouse, and that's what they're doing in this particular simulation. You can also do what's called SLAM, which is simultaneous location and mapping. So that would be, we wouldn't have a static map, and the robot would just start generating the map as it drives around. So the drawback, though, is the robot would first have to, in this particular contest, it's a guide bot. If the robot didn't know where the destination was, it wouldn't be able to guide them. So it really has to like have a map of the office.
So it starts to navigate immediately, right?
Yes. Yeah.
Okay. But then again, on the visual representation, it showed where it was, I thought. And I'm just confused about what we're looking at and how they relate.
In this, yeah.
Yeah, see there you've got the robot.
Yeah, the relation is tricky. So that's one of the points that a lot of people are unclear about. It took me a while to figure this out. But so this is not controlled. This is where the robot really is.
Maybe if you're sitting in a bleacher watching it.
Yeah, this is where the robot. So this is, think of this as the real world, and this is
The robot's
perception.
where the perception of the world.
Because the robot's not even close to where that pattern of blue is. The robot's over here where these big plus signs are.
So we can tell that we're troubleshooting. We can see the real world and say, hey, you're not in the right place, or you don't think you're in the right place.
It just hasn't figured it out.
Yeah, it doesn't know where it is. And that's what allows us to, that's the cool part about Gazebo, is you can see where the robot is, and you can see where it thinks it is.
Yeah.
And you can see that those don't match up, and then you can do whatever. That's where then you come in. That's your job as a robot, is to make the software that figures out where it is.
Deduce at that point that there's a bug or initialization problem or something.
So in this case, it's just part of the package that this robot needs a initial estimate. It's using ACML, adaptive, or AMCL, adaptive Monte Carlo localization. So it actually has I think we see the pose array. Okay, so all those red lines, whoops, I didn't want to do that, but that's all right. Those are where that's like, the way this localization module works it creates a whole bunch of guesses of where it thinks it is in the physical universe. And we can even see when it gets closer to reality, those guesses will start to converge.
Whenever you hear anything with Monte Carlo in it, think random numbers. Think random numbers. So it just randomly picks spots all over the map, and it sees how well it fits. And it finds the one that's statistically the best fit, and it'll take a whole bunch of points inside there and figure out of that set which one's the best, and it just keeps.
That's actually the way it goes.
That's the way it goes.
Yes.
It just takes a bunch of random samples and then says statistically I'm closest. This looks very close to where I'm at.
Wow.
Localization is hard.
Yeah.
So I'm just going to feed it in a guess about where it is, or tell it where it is. So now you can see, okay, so it's
That's why
much better. So you can see these lasers now start to line up, so it's got a pretty good idea where it is. It's still not really sure. That's actually a pretty big point cloud.
Yeah.
So what I can do is I can give it a nav goal. You'll see as this drives around, it'll actually get a little smarter about where it is. So I'll just give it a really short nav goal. You're just using the tools up here. And so what you're seeing now around it is the cost cloud. As it navigates, it kind of looks at all different paths of where it might go, and it weights those paths, and then it tries to find the best path inside the grid that it generates. So you can see now the red, all those red arrows are like almost a single point. Like at this point, the robot is already pretty sure of its location.
Those echoes it's getting back, right? The red lines are the echoes?
The little red arrows, like I'll turn off, let me turn off, I can turn off most other stuff.
Remember we did the SLAM thing way back, whatever? This is doing the same thing the localization's doing, it's just not doing the mapping. So it's taking all the external stuff and bringing it back to where it is, but it already knows where the map is, so it doesn't need to do...
It doesn't need to build a map.
Right.
But it is getting feedback from the sensors, and that's what I thought the red lines were.
Yeah, it is. That's where your hits are. It's ran the laser around and said, I think this looks like a wall, just like we did with SLAM.
So it draws it.
And it says that line statistically is that wall I already know is on my map.
Yeah, so these are, like if I'm showing it now, what I'm showing is just the laser, seeing the path that it was planning, which is not really feedback, but just kind of feedback for you as a programmer to see, well, what path was it trying, in case it ran into something, you can see what it was trying to do.
See the human up in the, above the green line, kind of come down.
I'll drive up there.
So to the right of where the robot is right now,
Mm-hmm.
that's a human, looks like, right? Because it's curved.
So it's getting that
So it would know, it could say that's probably a person.
Yeah.
Where it knows these straight lines are probably walls.
Probably, yeah. The software knows,
Yeah.
Yeah.
The robot
So,
would know.
yes. So, and then things like the static map aren't really, I mean, the robot, that's not really the robot's input, that's just, you know, we created a pre-created static map in this case.
Well, why shouldn't the robot be referencing that as it can?
It is.
It is.
Well,
It's just finding its own location in that map.
right, but once it's done that, it has the map. And it can now say, now I can make faster decisions based on different priorities here, because I'm no longer trying to figure out where I am constantly. I know where I am. I'm right in a map.
Right.
And I check every once in a while that, and my priorities become doing my job, whatever that job is, within that map, instead of wasting the energy.
CPU. You
Right.
can do that. I mean, you could say every, you know, just recalculate your position every 12 inches.
Right, whatever you need to do, or you could say, here's a safe, you know, we defined a safe area here, 12 inches.
Yeah.
And like, I'm gonna find pathways through here that I can use to optimize, just like I do when I'm walking down this hallway, I do the same
You
thing.
could do that. He's just telling it where to go, but you could have a higher level thing saying a goal, right, that says go to the bathroom, right?
Right,
So
but
you-
as soon as, I'm just saying, as soon as it recognizes that map, it can say, now I'm gonna go approximately 4 meters in this direction, now check and make sure I haven't run into that door in front of me.
But that's the
But,
problem. Did you really go 4 meters?
well, I
Or did a
realize
person
that,
walk
but
in
you are
front of you?
checking often, and as you
Yeah.
said, you check once a foot, but you're not spending time trying to navigate when you don't need to.
Yeah,
I
well, you
don't
can do
have
that.
to, you know, the door's there,
Yeah.
okay? I make a judgment based on that door when I get in proximity of that door to find that door handle.
Yeah. You
But
can-
I-
What about another person who's going through the door later?
Right.
Yeah.
That's why you gotta check
You don't know.
often enough. And as you
Yeah.
get closer to the door, you gotta check more often because your precision.
But I'm saying you're making no use of the map as it exists there as a tool at all. You're just throwing that map out there as something to look at. You're not using it as a tool to help
You are.
simplify the mechanic.
In this case, you're using the tool to find where you are
Yeah.
precisely in the
Okay.
map. But
So,
to your point, if
It's
a
literally
human
this
says,
instance that it's not.
Well,
different.
the map is used for navigating
right.
to different rooms.
So,
like
like
if
you
I
said-
want to send the robot, if I didn't have this map and I wanted to send this robot way over here, it would have no chance.
well, even if you had
It
the
would
room,
have
there's
to-
multiple paths to that. So you could say, I want to go to that room. You'd use like an A-star algorithm to do
Right,
the route
and that's
planning.
what I'm saying
Come up
is-
with the
is once you
general
have a
route
real-
through the thing. But then as you're walking, if you get an obstacle or somebody pushes a chair out, you know, you can realize that and navigate around it and still make your goal be the room.
Right, I'm just saying that that's just being underutilized as a tool, I think, because you're not, right now, that robot has a pretty good guess about where it is. You could check every option available and go, these are the 4 places I could be right now in this fixed map.
Yeah, but it knows
And
exactly
now-
where it is.
I'm just saying, but then you don't
Exactly.
have to do it anymore. For, not for a significant amount, robot-wise, a
Robot
significant
assembly.
amount of time.
True.
And go, now I'm gonna plan how I'm gonna get this little lady that's refusing to follow me to go into that room
Right.
over there.
Or the
Yeah.
person that won't move out of my way.
Well, most of these, I mean, I'm not getting into the software it's using. This thing is kind of designed.
Right.
They have some demo. This is a demo of how
Demo
you
software.
might
Yeah.
set up a robot to do this contest.
Yeah.
You can use your software however you want. So during the launch process, I actually launched everything at once, but you can launch Gazebo as one process, and then you launch your robots, all your robots code is another process, and then you launch RViz as another one to monitor all of that. So this is just like one working demo of how it might be. And then they have some interesting plug-in feedback for like humans have like RFID tags on them in this simulation, so your robot can actually read which human it's next to, you know, so if it's driving around looking for
California
somebody.
had started implanting chips in people's hands.
Yeah.
Yeah.
So, okay. Anyway, that's all I had, unless there's any questions.
Well, I still think